All right, guys. So let's move on to chapter 3. What's going to happen? This might seem like we're deviating from what we've been talking about, which we kind of are. We talked about 2 chapters of descriptive statistics, where we're talking about like means, medians, modes, standard deviation, variance, that kind of stuff. And now we're going to talk about probability. Okay, and we're going to revisit that from we talked about probability in algebra and geometry classes. Revisit it, talk about it in probably a little bit greater depth than what we did in those classes. Do that for a chapter, chapter and a half, 2 chapters, and then we're going to merge essentially the first 4 chapters together and start talking about statistics and probability together, and how probability allows us to make statistical inferences. You remember that there's 2 branches of statistics, right? Descriptive and inferential. Descriptive we've already been working on. Inferential is then using probability to make arguments. Okay. Question. Okay. You. So what we do here with after we learn probability is the idea that if I am a pharmaceutical and I create this drug for some type of illness, and I give it to a group of people, and let's say I give it to this class, and there's, let's say, 20 of us in here, and 10 of you get better, okay? Is that enough to say that the drug is effective or ineffective? And then what is then the probability that I give that drug to somebody that was not in the group? And what's the probability of them getting better? Does that make sense? Okay. And we'll talk about the idea of, sampling this drug to 20 people and getting the data off that. Is that ultimately good enough to produce validity in the effectiveness of that drug? But probabilities are going to kind of be the tool that allow us to say this treatment is effective or this treatment is not effective. Okay, but we got quite a bit of information to cover before we can get to being able to make kind of an argument like that. You guys all drive? Anybody pay for their own insurance? If you drive, let's say Lucas, and let's say Christina. Let's say you guys have the exact same birthday. That would be crazy. How many people in a room do you have to have before it can be guaranteed that somebody has the same birthday? 366. I'll guarantee it, right? Okay. So let's say that they have the same birthday, same exact age, all that kind of stuff. Okay. They go to the DMV on the exact same day. They get all their license and stuff and get approved to drive all on the same day. They go to the same exact insurance company. Okay. And they purchase the exact same insurance. Okay. Exact same, coverage. Okay. Meaning, if one of them gets in an accident, what is the insurance company going to pay in regards to fixing cars or bodies or whatever? Okay. Who is going to pay more for that exact same coverage? Why? Okay, so you say because he's a man, but go further than that. Why is being a man the differentiating? But why? Okay, so at that age, males are not, and it's like biological, they're not mature. Okay, females, by research, by science, females mature much quicker than males do. So the argument, and it's statistically based, is that the insurance company is going to have to pay out a claim on Lucas. The probability of that happening is higher for Lucas than it is for Christina. So therefore, he's got to pay more because he's more likely to have a claim. Does that make sense? You guys understand how insurance works? How's it work? I didn't say yes. Okay. All right. So let's say, if I wreck a car, how much a car cost? I mean, couple mil. All right, let's say you got some like if I go buy like a brand new 2020 car, okay? Um, yeah, let's just estimate 30 grand. And there's some that are I go buy like a Hyundai, it'd be like 18 grand. I go buy a brand new F-150 and it can be 70 grand. Okay, so let's just say $30,000. Huh. All right, so let's say a car costs $30,000. If I wreck it, okay, let's say I run into somebody else's car, okay, should they be penalized because I ruined their car? No. So I have insurance against that. I have insurance in case I ruin somebody else's car. Okay. And you'll buy like car insurance of whatever like coverage that you want. Okay. So let's say that I've got car insurance that will cover like $100,000 in damages. Okay, and usually you get coverage that's higher than that because it's not only is it physical damage to cars, but bodily injury to people. Okay, my premium might be $1,000 a year. Okay, well, how does $1,000 end up paying for a $30,000 claim? How does that work? What does the insurance company do with that $1,000? They invest it in the stock market and get a return on it. Okay. Now, whatever that return is might be, I don't know, maybe they make $10 off of it. It's not huge. Okay, depending on what they invest in. Okay. But now let's think about this. Am I all I've been paying insurance since I was 16 years old. I've never been in a wreck. So I've been paying this $1,000 since I was 16, right? And I've never had a claim. A lot of other people are doing that, right? Okay. So they might make a claim at some point worth $30,000. Okay. But other people who are not having claims taken out on them are still contributing to that fund. Does that make sense? And that's still growing, it's still getting invested, it's still making dividends. So that's how like insurance companies on a most basic level kind of operate and work. Yes. No, no, no. So they will invest. So that's a good question. Like an insurance company is going to make sure that they invest in like a mutual fund or something like that, so that they know they're not going to lose their butts on that. And the idea is that they're actually taking and they diverse it enough to where that they don't lose money. Now so that gets into a whole nother topic about the stock market. If you ever invest in the stock market, you're broke. If you do it with like an Edward Jones person, like a financial advisor or something, they'll ask you when you first go, and then actually ask it every year, what is your risk tolerance? Okay, are you willing to, if you're putting in, so let's say I have like a Roth IRA, okay, and you're allowed to deposit right now, I think the law is $5,000 a year into a Roth IRA, okay, and then they invest that for you into whatever stocks that you choose or that they choose, in hopes that money grows, right? Okay, so a Roth IRA, a lot of people use those for retirement. Okay, so I've got one, my wife's got one, and we're not going to touch them for like 30 years. Okay, so we're in for the long haul. So they'll ask you when you first start, they'll say, what is your risk tolerance? And they'll give you examples. They'll say, okay, if you put in $100,000 and in 1 year it drops down to $80,000, are you okay with that financially? Okay, because if I'm willing to take a risk of 20% loss, on the other hand, I'm also now asking that I'm okay with a increase in 20% as well. So not only could it have lost 20%, but it could have grew to $120,000. Does that make sense? Okay. So they'll ask you those types of things. Now, if you're doing it on short term, a lot of people are less risky. So I've got 529 plans set up for my daughters to go to college, okay? And we put money in those every month. And right now, I'm very risky with those things. I want those to – I'm willing to take a high increase versus a low or a high decrease, essentially. Okay, I'm okay with losing money on those right now because my daughters are, 16 years from school going to college, right? Okay, maybe not so much, 12 years, at least one of them. Now, the closer I get to her withdrawing that money, then I'll start to be more cautious on my risk. Does that make sense? Okay, if she's going to withdraw that money next year to pay for tuition, then I don't want to be real risky with it and say, yeah, I'm okay with a 20% reduction, or I'm okay losing 50% of that, because then that puts her in a bind for college tuition, right? So those types of things are all predicated off probabilities, and we're impacted by them, whether we know it or not. I mean, we're all impacted by the way the stock market fluctuates and the probabilities and the algorithms that drive that. For instance, the stock market today is down 900 points. That's a huge amount. It's like 3%. Okay, it's down 900 points because there's uncertainty about the coronavirus cases being in influx right now, and the stimulus to the House and Senate are basically saying there's not going to be a stimulus package. Okay, so there's uncertainty there. So stocks don't like uncertainty because the algorithms and eventually even the people that do the day trading don't like uncertainty, so they start trading money away. They start withdrawing from those stocks and that kind of stuff. Does that make sense? But that $900 drop is all based off the probability of what could happen. Okay, but we're all impacted by that stuff. So probability impacts us a lot financially. If you have an illness and, every time I have an illness and I go to the doctor and get a prescription, I'm taking the chance that prescription is going to help me. It might not help me, right? Has anybody ever gone to the doctor and gotten medicine and taken it and you've gone through your whole cycle of medicine and you still have the ailment that you went there for? Okay, it happens. Medicines aren't 100% foolproof, but there's a high probability that they're going to work for you. Flu vaccine. Anybody got the flu before? After getting the flu vaccine? Okay, make sure you do. So if I believe like the average for a flu vaccine is like a 60% effectiveness rate. Okay, meaning that I go get the flu vaccine, but I still got a 40% chance that year to get some strain of the flu. Okay, they're saying that they will be happy, they will exceed kind of expectations if the coronavirus vaccine is 50%. Okay, so we've got probabilities that are built into those things, and people are, can I go get a shot with a vaccine that may or may not help me? I know because of the flu vaccine, I know there's no really long-term effects, negative effects of getting that. Might as well take the chance to get it. At least I protect myself with that 60% of probability. Does that make sense? Okay. There is a low probability. Okay. Some people do get vaccines and then die, right? One of the big things is like anti-vaxxers right now with children is thinking, okay, is there, and there's a lot of research on both sides of this, is if I go get my son, daughter vaccinated when they're young and they get their cycles of vaccines when they're born, like 6 months and 1 year and 2 years and stuff like that, that they become, that vaccine creates or influences autism. Okay. A lot of research, a lot of studies done on that. Okay. But it's all probability. It's all understanding how the probability in those studies allows people to make decisions. All right, so key terms here. Experiment, okay, is a planned operation carried out under controlled conditions, okay? Now, when we start talking about probability, you're going to start thinking maybe, what does this have to do with like all these studies and everything we kind of talked about in chapter 1 and 2 about research being conducted in controlled variables and response variables and explanatory variables and all that kind of stuff, Okay? What I want you to understand is that we're going to investigate and try to gain an understanding of probability based on things that we are right now understanding of. Flipping coins, pulling cards out of a deck, names out of a hat, marbles out of a jar, those types of things. We investigate probability that way. And then we'll make the jump to how does that probability and what we understand there, how does that work inside like medical research and those types of things. Okay, so we'll make that transition back to the real application stats, because nobody's sitting in a room and really worried life-altering examples or situations of, what's the probability that I pick an ace out of a card of decks, or that doesn't make sense, a deck of cards, if I've already picked out an ace. Okay, that's not life-altering for anybody, right? But understanding how that probability works will allow me to transition into how we can actually apply the probability inside like life-altering situations. Okay, so we know we're familiar with flipping coins, rolling dice, rolling cards. Those are experiments. But another experiment might be giving a particular drug to a group of patients. Okay, an example might be There might be an experiment that deals with kind of observing the collision rates of 16-year-old males versus 16-year-old females. Okay, so those would be experiments. Outcome is a result of an experiment. Okay, so if we're talking about the collision rates, and the result of an experiment there would be, was there a wreck or was there not a wreck? Okay, flipping a coin, is there heads or is there tails? Rolling a dice, my outcomes would be 1 through 6, right? But when we talk about an outcome, we're talking about the individual result. Okay? When I talk about the sample space, that's a collection of all of the individual results. So if I'm talking about rolling a dice, a 6-sided dice, okay, and this class, you'll see examples that talk about different sides of dice. If I just say dice, it's the normal dice that you play like Yahtzee with, right? 6 sides, okay? If they want something else, they'll call it like a tetrahedron or something like that. Okay, they'll talk about the amount of sides versus that. What? You might say dodecahedron. Okay. So if I say dice, just 6 sides. So if I talk about the sample space for a dice, it's 1, 2, 3, 4, 5, and 6, right? It's all of those outcomes collectively. If I talk about the sample space in a deck of cards, it's all 52 cards collectively. Okay, an outcome of 52 cards would be like the ace of spades, okay, or the queen of hearts or something like that. Those would be individual outcomes. Does that make sense? Okay. A lot of times when we talk about sample space, so we're going to do, and we'll see a little bit tomorrow, identifying sample spaces, identifying sections of sample spaces or sets of sample spaces. When I write a sample space, we use a capital S, okay, and then we put equals and then curly braces, because those curly braces refer to mathematically a set or a collection of objects. In this case, the objects are our outcomes, okay, our potential outcomes, and they would be, in this case, H and T for heads and tails, okay. If I was talking about the sample space and I wanted to write it for rolling a dice, it would be capital S equals curly brace, 1, 2, 3, 4, 5, 6, curly brace. But that's how we refer to sample spaces and listing sample spaces. It's not a huge deal when we do things by hand in here, but if we're reading something on Math Excel, reading something in another text, and they use that, that's what they're telling you. An event is any combination of outcomes. So let's say I flip a coin and I say, what is the probability of it landing heads? That would be an event. It's a combination of just the one outcome, landing heads. If I ask you to roll a dice, and I ask you what's the probability that it lands greater than 3 and odd. Okay, so that's a combination of greater than 3. That's one outcome, one grouping of outcomes. And odd would be another grouping, right? Okay, so how many numbers are greater than 3 and odd on a dice? 1. Which number? 5. Okay, so it'd be 1 out of how many possible outcomes? 6. So the probability that'd be 1/6. Okay. If I flip the coin and say what's the probability of it landing heads and tails at the same time? Can't happen, right? Okay, so it lands with a side up, and I ask what's the probability it lands heads and tails being the outcome, okay, or the outcomes, combine those, and that's the event. That cannot happen, okay? All right, so uppercase letters represent events a lot of times in just identifying or defining our probability formulas. They'll use A and B as our events. They're just arbitrary, generic situations, okay? A lot of times it might make sense if we're flipping a coin to use H and T. If we're rolling a dice, use 1, 2, 3, 4, 5, 6. If I'm talking about, collisions, okay, maybe I say W for wreck and I say NW for no wreck. Does that kind of make sense? Okay, so our labels that we use should be indicative of the situation that's taking place. Just some things about probability. The definition of probability is any outcome and the long-term relative frequency of that outcome. Okay, it's the long-term relative frequency of that outcome. You guys have probably thought about it or learned about it as the likelihood or the chance of something occurring, which is exactly the same thing. Okay, probabilities are between 0 and 1. Inclusive, meaning you can have a probability of 0. If I flip a coin and say what's the probability it lands heads and tails at the same time, probability 0, right? A probability of 0 means it cannot happen. Okay, a probability of 1 means it's going to happen. If I say I flip a coin and what's the probability that it lands heads or tails, well, that's going to be 1, right? It's got to be 100% of the time. One of those is my options. Okay, and if I have a 0.5 as my probability, that means that the event A is likely to occur or likely not to occur. Okay, if the weather station has a 50% chance of rain today, might rain, might not rain, right? 30% chance. Now we kind of understand that a little bit better, right? Less likely to happen. But if it's 50-50, it's equally likely to occur or not occur. Equally likely, again, and this is where we start to kind of make connections to what we've already talked about in the past. In the last chapters, when we talked about things that were equally likely to occur, what we were interested in was taking a sample, and each person or each object in that sample, we wanted it to be equally likely to occur as any other. Does that make sense? So if I take this class, 20 people in here, and I'm going to choose a sample of 3, and let's say I put Lucas in there, Lucas gets added in there, I want Lucas's chance of being added to my sample to be equal as Brooklyn's chance to be added to my sample. Does that make sense? Okay. So when we choose samples, we have this idea of equally likely to occur, and there's your link to probability, or a link to probability. Okay. If you roll a fair dice, okay, each face is 1, 2, 3, 4, 5, 6. So equally likely occur means 1 is going to occur 1/6 of the time, 2, 2/6 of the time, 3, 3/6 of the time, and so forth. Okay. 3, 1/6 of the time, 4, 1/6 of the time. I think I said 3, 3/6 of the time. Sorry. So 1, 1/6 of the time, 2 is 1/6 of the time, 3 is 1/6 of the time, and so forth. So to calculate probability of events, when all outcomes in the sample space are equally likely, you count the number of outcomes of event A and divide by the total number of outcomes in the sample space. Okay. So we'll get into a lot of examples with that later on. In this first section with terminology, I do have some examples that are written. I'll let you guys read those. But I'm more concerned right now just getting the terminology kind of understood, and we'll get to the examples in more specific scenarios later on. Basically, what this first section is, 3.1, once we get through it, I'm going to introduce a lot of things here, but that kind of sets the other sections up for us to discuss those other sections. So, like one of these, we're going to talk about Venn diagrams and tree diagrams at some point in this first section. but then we further investigate those in their entire section in 3.5. There's an entire section devoted to those two things. Okay. This is just introducing the concepts. All right. So theoretical probability. Okay, and this is kind of what we usually kind of play off of initially when we start learning probability. If I ask you, what's the probability of choosing an ace out of a deck of cards? The theoretical probability goes off of mathematical calculations that we know. Okay, how many aces are there in a deck of cards? 4. There's 52 total cards, right? So mathematical calculations tell us that there are 4 out of 52 ways, right? Which reduces to 1/13. Okay, so that would be my theoretical probability. Okay, if I were to flip a coin 10 times, what is the probability that I get 5 heads and 5 tails? Theoretically. Let me ask you this. If I flip a coin 10 times, theoretically, how many heads should I get? 5. Okay, how many tails should I get? 5. But we're all aware that we could actually do that experiment and maybe get 7 and 3 or 10 and 0, right? Okay. This morning, it's kind of bizarre. I never thought this would happen. This morning, I was creating an Excel sheet for us to manipulate a little bit tomorrow. I don't have it open anymore. But basically what I was doing, we can do a simulation that basically Excel generates a 0 or a 1 randomly. And we call zeros heads, and we call ones tails. So basically, Excel will flip a coin for us. Does that make sense? And as I was doing this, so I created my first cell and flipping heads or tails, and I dragged it down 10, and it flipped my coin 10 times and landed heads each time. Okay? That's a very, very low probability of happening. Okay? Basically, that's 1/2 to the 10th power. Okay? Which is a very, 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 very small number. But it happened. But we know that if we're doing that on our own, it could happen. But theoretically, we should get 5 and 5. Okay? Theoretical probability a lot of times is referred to as expected probability because that's what you expect, right? If I flip it 10 times, you expect to get 5 and 5. Okay? Doesn't necessarily happen, though. And when it doesn't necessarily happen, that's when we get to what we call the experimental probability. Okay? Experimental means I'm actually doing the process, right? I'm actually flipping the coin, okay? Or I'm actually administering a drug to a group of patients and monitoring what's going on, okay? A lot of times it's called empirical probability. We had a word empirical in the last section, right? Last chapter, okay? There's a link, okay? Empirical, talked about that normal curve, right? That normal distribution. Okay, when we do an empirical probability situation, we actually run through the experiment. Our goal is to create our sample so that it is normally distributed, okay, or as close to normally distributed as possible, so we can use that empirical rule that we learned in the last chapter to make predictions, to use that inferential statistics. It says when you conduct hands-on experimentation, in other words, you get your results from actual experience rather than from a theory or a belief, okay? I was writing some notes here for later on in upcoming chapters or section. One of the examples here says, a college reported the following based on their graduation data. So 70% of freshmen had attended a public school, 60% freshmen had attended public schools but graduated within 5 years, and 80% of freshmen went to other schools, not public, and graduated within 5 years. Okay, so that is like an observational study, which kind of matches up to the experimental probability situation here. Does that make sense? Okay, there's not formulas or mathematical calculations that we generate these 70, 60, and 80% from. Okay, where there are mathematical calculations where I get like rolling a dice 1 out of 6 or pulling a card 1 out of 52. Does that kind of make sense to everybody? Okay. Now the idea, so empirical probability refers to observed probabilities. That's kind of what I just talked about there. These two things they're most definitely probably different. Okay, theoretical probability and empirical probability or experimental probability for a certain situation are different. If I ask you what's the theoretical probability of flipping a coin 10 times and getting how many heads, I should get 5 heads and 5 tails, right? Experimentally, though, we might get 7 and 3, 8 and 2, 9 and 1. Those are different. 90% heads and 50% heads is different, right? Okay. Well, what happens is what we call the law of large numbers. The law of large numbers says the more you do that experiment, instead of flipping 10 times, you flip it 20 times. You flip it 30 times, 40 times, 50 times, 100 times, 1,000 times, million times. Okay? The more you do an experiment, the more aligned your empirical probability or experimental probability aligns itself or equates itself to the theoretical probability. Does that make sense? Okay, so we'll do that a little bit tomorrow with an Excel simulation with flipping a coin, or maybe we might even, depending on the time we have, alter a little bit and roll a dice. Okay, but the idea then is, okay, how does that help us in like a statistical research scenario? If maybe I'm analyzing, like I said, we always go back to the farmer, so I think that makes sense to us. We're talking about medicines and stuff like that. If I give a vaccine to 15 people and 10 of you get better, is that enough to say my vaccine is 66% effective? If I gave it to 10 out of 15? Well, it reduced to 2/3, right? 66% effective then, right? Okay, so what we want to do, so that's my experimental probability, right? And I only gave it to 15 people, okay? That's not going to be enough data to validate, what an idiot, validate, I do that a lot, to validate my results, okay? And to be able, as a pharmaceutical say, or even the FDA, to say, yes, this vaccine works. This is an effective vaccine. So what we do is we apply the law of large numbers, which the law of large numbers says get more people in your study, right? Okay? And then the more people you do it to another group of 15, and then another group of 15, another group of 15. And eventually, instead of giving it to 15 people, you've given it to 1,500 people. And you start to take the results that you see out of that 1,500 people, and now we can say, okay, now this drug is effective or ineffective. Does that make sense? Okay. And then eventually we can do what we call hypothesis testing to even be more convincing with whether it's effective or not. Okay, and we'll talk about that later on. Does that kind of make sense? Okay, and how my hope is that we see flipping coins, doing probabilities, doing experiments that make sense to us that we can visualize easily, and then how that's going to then transfer over to, working in like a medical research study, or I've given you the example of when I wrote my research for college that I did like one-on-one computers, okay, whether that was effective or not effective, okay. So we'll make that transition as we learn more about probability to be able to do that. Is that cool? All right, so tomorrow we're going to start off with that Excel simulation.